let's look at the compressor first. So, we have low pressure fluid at the inlet, and by the time we get to the outlet, it's going to become highly pressurized fluid. This process requires some work since you can't just make something go from a lower pressure to a higher pressure. The turbine is going to do the opposite. So it takes in highly pressurized fluid or liquid and expands it. So by the time it gets to the outlet, it's going to have a smaller value of pressure. This process is going to rotate the blades of the turbine and generate some work out. So we can actually extract power from turbines. Now, if we call the inlet of the compressor point 1, outlet of compressor 2, inlet of turbine 3, outlet of turbine 4, we now have 4 points that we can plot on our TS diagrams. So we can plot them in terms of temperature and entropy on these faint green lines, which are called pressure lines. So let's do it for the compressor first. At state 1, we have lower pressure fluid than at state 2. So we're going to draw it on the lower pressure line, the bottom one. And we actually have to plot point 2, which is for the actual process, and point 2s, which is for the isentropic process. Now, what makes a process isentropic? 1, if it's reversible, so no heat transfer, and 2, adiabatic. So the entropy at state 2, S, has to be the same as the entropy at state 1 for the isentropic one. For the ideal process, so entropy at state 2, has to be greater than entropy at state 1 because the actual process is irreversible, and for irreversible processes, entropy always increases. Remember that. Entropy always increases for irreversible processes. Entropy is always constant for the isentropic one. So, let's plot this one. If the entropy has to be the same, by the time we get to the second pressure line, we can just draw a straight line and get point 2. Point 2s, the isentropic one. And since we said the entropy always increases for the actual process, on the second pressure line, we're going to have to plot a point slightly higher. So from point 1 to point 2, another straight, more oblique line. Okay, now for the turbine, same thing. We have to plot point 3, and we know point 3 is going to be more highly pressurized than point 4. So this time we draw this on the top pressure line. And we're going to have to plot point 4 for the actual process and point 4s for the isentropic one. We remember that for the actual process, the entropy always increases because it's irreversible process. And for the isentropic one, entropy is always the same. So if we plot the isentropic one, once again, we can just draw a straight line, and you see the values are going to be the same for both, and we have 0.4s. Now 0.4, we said entropy always increases, so from 0.3, we want entropy to increase. So on the other pressure line, we're going to have to draw it slightly more to the right, 0.4, and draw them up from 0.3 to 0.4. Okay, now we can write the isentropic efficiency for the compressor and the turbine. You can see it's literally going to be the opposite of the other. So how do you not confuse them? How do you not muddle them up? That's why this is useful, because you can write it in terms of enthalpy. So basically, one thing to remember first of all is that the isentropic efficiency for the compressor is going to be 80%, and for the turbine, 100%. This is the isentropic efficiency. If you think of this in decimals, it's always going to be smaller than 1. And from maths, you know that if your values is smaller than 1, the numerator has to be smaller than the denominator, which in our case is different for each one. And looking here, we can see the difference in enthalpy. So you plot on the numerator the smaller difference, basically due to the smaller length, over the difference from the longer length. So the shorter length is h2s minus h1 on the numerator, h2s minus h1, and on the denominator we have h2 minus h1. Usually the formula would also have to be multiplied by the mass, because work is mass times by some difference in enthalpy, but we can just cancel out the masses since we're, simplifying. Now, for the turbine, once again, we want the shorter value on the numerator, so basically the difference in the shorter length for enthalpy. So h3 is the higher one minus h4, divided by the longer length for the numerator. So h3 minus h4s. You can't really tell which one's longer, but if you just draw a horizontal line, you can see this is slightly longer. And that's it.